Okay, so now the record is on. So today it's about the additional limit states or failure modes, the way your beam can fail, in addition to what we have discussed about up to this point. So let's say if you have the beam, maybe blue would be better. Yeah. So if you have the beam, okay, generally what happens when you have the beam is that you're going to have the to check the bending moment, right? With the local buckling, of course, always an issue, and then the moment itself. Okay, that's moment, too small. Let's do it again. Moment. And then shear. Now, don't forget that for shear, you always have to check the local buckling as well to make sure that, you know, you got that 0.6 Fy multiplied by the area of the web. Okay. And then serviceability or displacement. And these three stuff are basic stuff. However, let's say when your beam has to carry a point load. Okay. Point load officially is called the concentrated load. Okay. So, oops, I'm sorry. So let's say concentrated load. Or, well, I should say point load because it's a lot easier to pronounce. Okay. But you should know that if you go and read the textbook or look at the specification, it says concentrated load. Okay. Can, or maybe I should say may, you know, may cause additional failure mode. Okay. Now, let's say sometimes when you put the beam on the support that say it's some kind of an abutment, okay, concrete abutment. If you don't know what it is, in Thai we call it tò mò, or you know, concrete footing or something. Say concrete support, which can be footing or abutment. Now again, if you are true to the free body diagram, it doesn't matter what kind of load your beam carries, but the reaction here, reactions do become point load as well, right? So whenever you have the point load, the additional failure that caused by the point load may occur in your beam. So if you have a point load, keep in mind that not only these typical failure modes that you have to consider, you have to also consider additional failure mode due to the nature of this load as well. Okay, it's in addition. Okay, so the first one that can occur is called web local yielding. So it says here yielding. So in fact, your beam web can yield under the point load. Now this generally means it's both compression and tension. Okay, now there is a good mechanism that we can look at and understand what's going on. Let's see, I don't have the picture here, so I'm just going to have to draw it again. So let's say, first one, we web local yield. All right, so here, let's say if this is your beam, and you now have the concentrated load or point load applied. But again, we always draw the point load on paper as an arrow, like a dot, an arrow applied on a dot. But in the real world, your point load must come with dimension. So let's say if your beam is going to maybe support some vertical member coming down with a load, it has to be attached to your beam by some kind of a plate. So this plate becomes the area where your load acts on. Okay, it is a very small area. That's why we call point load. But in fact, the load comes in with some dimension, but it's not large. Okay, it's not on the entire beam. In the old days, I believe that here I call it N. So they call it N, but now say they change. If you look at the most recent specification, they change from N to call LC. It's the same thing. Okay, so the load comes in with the dimension N. Now this is the side view, understand that? We are looking at the side view of our beam. So the load comes in like this. It's going to cause yielding to your beam web. But the thing is this. Damn it. I wish to move this guy because I need space. Yeah, okay. Okay. The load is going to come in like this. But, once you have the load acting on your structure, do you think that the stress is going to go down directly? Say if I have a plate like this, is the stress going to go down directly like that? It's like when you step on the ground, you think the stress from your foot on the ground will go directly like that? No, it isn't. It's just going to have to be distributed out to the side like that. Okay, so this is going in that fashion as well. And from the research, they have sort of discovered that the slope here is 1 to 2.5. Okay, it's just going to come down to the location of your web. So if I draw it like that, I draw this beam in the front view fashion, you will see that we have the fillet, right? And this is the beginning of your web. And this is K, remember? And K is basically equal to the thickness of your flange plus the radius of your fillet. Okay, so make notes that this is a fillet. Okay, so that means if this one goes down 1 and goes to the side equal to 2.5, if it goes down K, this becomes 2.5 K. And another side is also 2.5 K. So we have N in the middle and 2.5 K on each side. So that becomes the length that your yielding is going to occur. Now to make this into the area, we must multiply that by the thickness of the web, right? And therefore the area of the web that may yield simply is 5K plus N. All right, so that becomes the area. So you multiply the area by the stress, you get the force. So that's exactly what we have here, you see? N plus 5K multiplied by the thickness of the web and then multiply by Fy. So that becomes a web local yielding under, see, the concentrated force or the point load. Okay, but there is another condition, right? Let's see if we look at this beam and this load N is at the support. Okay, the same picture is going to happen, but this time, if I draw the support, you see this time you only have one side of distribution. See, so that the area is only here. So if you have one side, it means that you only have 2.5K from one side and then N. So then this area, because of the limitation caused by the fact that your load is at the edge of the beam, you now only have the area of 2.5K plus N instead. So you go back here and you see that we have another case where your area is down to N plus 2.5K multiplied by the C web and then F1. And this is when this load is applied at the distance less than D from the end. So I can draw it here, show you that for the beam, if the load is the support reaction, you see it's right here at the end. So it's in this case. And let's say to demonstrate this more clearly, let's say if this is the beam edge. Oh, it's a tiring morning, so my hands pretty shaky. Let's say if this is your P, and then this distance, if this distance is less than D, and D is the depth of your beam, of course. So whenever the load is so close to the end of your beam that the distance from the end of your beam to the load is less than D, your capacity is down to this. So it's basically a half of 5K. Okay. And this is the one and only case where you have reduction factor of 1 and factor of safety of 1.5, not by accident, just like this sheet. And this is simply because when they were doing the research, they were looking for the next failure mode, but then they discovered this failure. And they were so sure about everything that the second one is much more, say, critical. And then it may happen before this one. And they're pretty sure about it. So that's why they use these factors, okay? And this one can be explained by the design model that I show you from this picture, okay? But the second one, which the one that they were looking for, unfortunately, cannot be described by any design model. It's called web crippling, okay? It's called crippling, it means that the load is here. And this load is so large that it causes buckling in your beam web like that. You see, and they call that crippling. Here's crippling. So it does say concentrated load, but this has to be compression only. Okay, tension cannot cause the beam to buckle like that, the beam web to buckle like that. So it has to be compression only. Okay, so let's say if I have a beam like that, and I have the load hanging from the bottom of the beam like that, this beam can suffer yielding but not crippling. So if it's tension like this, crippling doesn't occur. Okay. All right. So here's the formula for it. You see, it's pretty, you know, it's the formula that I don't feel proud of to say about it, because this is essentially the curve fitting formula. They did a lot of testing and then they tried to match the test results by a curve, and this is the formula to explain the curve. Okay, maybe it's time that they change the formula, but maybe somebody haven't thought about it because, you know, maybe it's not that big of a deal. But anyway, this is the formula. And keep in mind that, again, if the load is not near the end of your beam, this is your formula. Okay, be mindful when you use your calculator because you can easily make a mistake here. Okay, but if the load is so near the support, like the one that I just drew, if it's so near, but this time, if this distance, I'm trying to write the same thing as this one, okay? Yeah, if this distance is less than d/2, see that's a difference, okay? They allow only d over there, but here is d/2. So if this distance, from the edge of the beam to the load is greater than d/2, then you are, excused from checking this failure mode. But if it's within, like the support reaction that we had, we now have to consider slightly further with two cases. Now you have to check the ratio of the end distance, or the LC, over the depth of the beam. If it's less than 0.2, you use this formula. If it's greater than 0.2, you use another one. So that must be the issue with the curve fitting as well. And you see, if it's the case, you see the coefficient is down to 0.4 compared to 0.8. See, so this is a typical formula. This one is a typical formula. Now, when the load is near the edge of the beam, you are down to 0.4, and the first one still looks similar. Then when you have N over D ratio greater than 0.2, you have to change the formula. And this is the quite critical failure. So they use factor of safety equal to 2 and reduction factor of 0.75. So whenever you have the point load or concentrated load on your beam, these are two additional failure modes that you must check. Okay. Now we move on to another issue, because I mentioned that the beam can be put on the concrete, and we always have to connect the steel structure to the concrete somewhere, somehow. Okay, so you can say that the steel has to be connected to concrete. Most of the time, let's say when you have the steel building, you cannot have the steel foundation, right? Because of the exposure to the soil conditions and so and so. So even if you have steel columns coming down, when you want to connect your steel column to the foundation, the footing of the foundation has to be concrete. And part of the footing, you have the abutment, correct? So I can maybe a new page would be better. Okay, so let's say you must have concrete footing. And generally, I used to ask many experienced site engineers, why do we need to have abutment? They said, no, we actually don't need to have abutment. This part is called abutment, or tomo, as I mentioned. And the concrete must, the steel must come down and connect to this abutment, or sometimes right there on the footing. Okay, but regardless of whether you connect the steel column to the concrete, whether it's an abutment, whether it's a footing, you need to have what we call a base plate. Okay, so this is a base plate. All right, simply because most of the time you cannot have the very smooth surface of the concrete, especially, and then of the steel. So we need to have this base plate to help adjust the leveling of the columns. Most of the time, they would install some kind of anchor bolts in here. If it's like that, they call J bolt. All right. And when they have the J bolt over here, they would best install during not during, before casting. So it's there, you know, when you cast the concrete, it's there. And then base plate. Oh, not base like this, sorry. Rough morning. Best installed before the casting the concrete. So when you have the bolt there, you know, you bring the column, which is already welded to the base plate, and then you put them on here, and then you adjust the leveling with the bolts and stuff. Okay. Welded to column. So keep in mind, you know, that the size of the plate should always be greater than the column itself. Right? This is the practical issue that many students missed. Let's say if this is something like your column footprint, your base plate will always have to be greater than the column, okay? To ensure that we can actually construct it. So base plate, practically, should be greater than, not greater, bad word. Should be larger than the column footprint. Okay, now, because we all know that steel is stronger than concrete. So when we try to attach the steel structure to the concrete, we have to be concerned with one or two things. First of all, we must make sure that because material-wise, steel is stronger, so we must make sure that the concrete will not fail. Okay, and most of the time when the load comes down here is compression. So we must make sure that the concrete here has the area big enough to withstand that compression. Right, so first one, we must make sure that our concrete will not crush underneath the compression. We prevent this by providing the area big enough. Big enough. The second is that when the things come down like this, you know, if the concrete is large enough but still in the contact area. So again, if I draw the base plate, so this is the base plate. Naturally, when it comes in contact with the concrete, put some rock in it so that you feel like this is concrete. The stress will occur, right? Because you have compression coming down here like this, and therefore the stress will go up like that. All right, to complete our free body diagram. So this stress will bend the plate. Bending occurs. So the plate will bend. Okay. Now we don't want the plate to fail by bending. So when we look at this failure, we are saying that we will prevent this by providing the plate that is thick enough Okay, so two issues really for the column base plate. The first one is that you must have the area of the concrete that is large enough so that the concrete will not crush under compression. The second is that you must have the plate that is thick enough so that the plate will not fail under bending moment that is caused by the pressure coming from the concrete. Okay, so basically what you should be able to see is that when you have the area of the concrete, you will be able to calculate that uniform stress. This one, right? Bending occurs due to this uniform load. Okay, say uniform load. This uniform load you can calculate once you know the area of the concrete. Okay. Can be calculated once the area of the concrete AC, okay, is known. So it's a pretty simple step, really. You calculate the area of the concrete to prevent the concrete crushing first. Once you know the area, you can calculate the stress based on the basic formula, you know, force divided by the area. You have the stress, you can use the stress to design your bending. So naturally, yes, if your area is large, it's going to help the plate as well. Okay, so there's another issue because if, let's say, instead of the column base plate, let's say if we have a structure that looks like this in the picture. So in case you want to put your beam on the concrete, you must have the base plate as well to help adjust the level. And you have to design this concrete that is big enough so that the concrete crushing will not occur, you know, underneath the reaction from the beam. And then you have to design the thickness of the plate to prevent the plate bending as well. But in addition to that, because this is the reaction on your beam, right? So again, these two things will come into play if you have the base plate to support beam, but columns will not have it. Okay. Any question then? No question. All right. So here's the design model. So let's take a look at the concrete first. The plate first. Okay. Now, as you can see, this is the plate that supports the beam, right? The plate that is going to bend from some distance, and in some part of the beam, we can assume that it is going to act as a support. So that this plate, this strip, you can see, it's going to be basically just like a cantilever beam. Because let's say this area, you see, this is the very rigid area because we have the connection of the web with the flange, and we also have the fillet. So we will consider this as a cantilever beam. See this blue one beginning at this distance end. Okay, becomes this design model. See, that is the end. So the end basically is equal to the width of this plate minus 2K and then divided by 2. See, I was confused with this K distance as well because they use the K in the vertical one and then apply in the horizontal direction. So if I am going to expand this picture a little bit. Maybe like that, okay. Erase that. Now we know this is K, right? This is your K. So they are saying that if this is K, they are saying that, okay, you can consider this K as well. Okay, so this becomes the cantilever beam that you must make sure that, you know, it will survive the bending moment. Okay, now this is the cantilever beam, but I draw the picture of the beam. And now I have to move this down. The length that you actually have to design for is the length of this plate. Okay, and that is K, and that is why, you know, it's the entire length minus 2K divided by 2, or you can just say if you measure everything to the middle, that is half the width of your plate, right? Then minus K, it's the same thing. So this is the model that we used, and we can calculate the stress that's going to be acted upon this beam coming from the reaction divided by the area of the plate, BNUC. So now you have the cantilever beam, and you know, we have the Thai word for it. I have never seen any English word for it, which says we turn things upside down, because you see this is coming from underneath, right? And when you turn things upside down, you have yourself a cantilever beam. See, and that becomes the length, which is B over 2 minus K. And this is your F, which is equal to the reaction divided by the area of the plate. So that is your bending moment. Okay, is there any question? Oh, crystal clear, maybe? Now, the next issue is the concrete crushing. Okay, let's say the blue area here is the area of your base plate. Okay, again, just like the concept in the web yielding, when you have the load coming down, the distribution of the stress is not going to go down like a straight line. Okay, so I have to draw on a picture maybe. When you have the plate, let's say I draw the area of the concrete very large this time. Okay, the stress, let's say you have the load coming down here, the stress distribution when the load is transferred from the steel base plate into the concrete, it's not going to fail right here as well. So the stress will go down. And it's going to fail somewhere down there. Now, from local web yielding, we are saying that the slope that we use is 1 to 2.5, right? But in concrete, this slope becomes 1 to 1. So if I draw this top view, it means that the distribution here will go out like 45 degrees in each direction like this, until it hits the edge and it cannot go anymore. Okay, but this area where the failure occur, you know, the area of the base plate is called A1, base plate. The area underneath here is called A2. Okay, so A1 is essentially the area of the base plate itself, but A2 is the area where, you know, the concrete failure is going to occur. And A2 must always coincide with A1. So it have to be of, you know, the same shape, and they always have to coincide, which means that their centroid must be at the same place. So for example, if this is my A1, my A2 cannot be like this. Let's say if this is the edge of the concrete, something like that. This is wrong. If I have the A1 like that, and that is the edge of the concrete, same, I'm using the same scale. This goes out 45 degrees, so it hits it here. It hits it here. So that means this can go out the same distance, and that will become your A2. Now, like this, the two areas coincide. Okay, but you can see that this is the design model that they use. But somehow, let's say you sit your column or your beam on a very large concrete structure. We cannot allow the A2 to go on forever. So there must be a limitation to it. And they put the limit where A2 must not be greater than 4A1. That's the limitation. Okay. In other words, the spec would say this: square root of A2 over A1 cannot be greater than 2. Okay, that is why we have this formula. So essentially, the strength of your concrete is 0.85 FC prime multiplied by A1. Okay, and then this ratio of square root A2 over A1, just to see how much you can have for the area that the failure is actually going to occur. And the most that you can have is 2. Okay? That means, you know, once you hit the area of A2 equal to 4A1, you cannot go further. That is your upper limit. So pay attention to this limit. Yeah, I should use the word concentric. That would explain it better. They must share the same centroid. And you cannot go beyond 4A1. So if you put either the column or the beam on the concrete foundation, for example, you cannot utilize the entire foundation area to support the this. Okay, and it makes sense because let's say if the area of the concrete is so far away from where your steel structure is, how can it help support the load, right? So this has to be limited to this. All right, and plate bending, last one. Now remember, we have the design model. Now we can calculate your moment. Now this is based on 1 unit of your plate width, okay? So let's say your plate is long in whatever direction that you may have. We can design this plate by assuming that, okay, the width of this is 1 unit, and you can design the strip of 1 unit here. Okay, and when it becomes 1, it means that your bending moment is simply this, right? Stress, which comes from the load divided by the area of the plate, multiplied by L square over 2. Basically, it's WL square over 2. Okay, it's either this, or if you're more comfortable turning things upside down, you now have this model. And then this is FP, this is your N, which we discussed this previously a few minutes ago, that this is the length that we are going to use, that we are, because we assume that the plate is going to be bent over this. This is the rigid zone where it will act as your fixed support. Okay, so basically this is WL square over 2. Okay, and now that's the demand, right? The external moment. Now for the moment of the plate, see, we are going to use the plastic capacity of the plate, which is equal to Fy multiplied by plastic section modulus. And now, because you see, this becomes the cross section of your plate, right? So from this, the plastic section modulus of a rectangle, that is TP, right? And we consider the width equal to 1. So it's BD square over 4. So 1 multiplied by TP square over 4. So now you have plastic section modulus, you have moment, you make them equal, and you can now design your plate thickness. So this equation, actually, you don't have to memorize it because they come from here, FP N square over 2 must not be greater than the plastic Fy, and then plastic section modulus, which is TP square over 4, and then divided by, divided by factor of safety. But you know, factor of safety is 5 over 3. So when I write like this, instead of writing like that with 5 over 3 as the denominator, I can swap the, because 1 over 5 over 3 is 3/5, right? And that's 0.6. So I can instead write 0.6 here. Okay, and when I arrange this, because the TP and N are both square, right? I can rearrange this, and this is what I get. Okay, so essentially it's from this equation. And this, you just change the 0.6 into 0.9 because the phi is 0.9. If you're confused, again, is FP N square over 2, that moment cannot be greater than 0.9 Fy, and then plastic section modulus TP square over 4. And this is your reduction factor, and this is this. Okay, any question? Now that is the length for your cantilever model to design the plate thickness. When it comes to column, we are going to use this model instead. We are going to say that the green area here is the solid area. So you have a cantilever beam model on 2 directions. First one is this one, where you assume that the cantilever length is going to be this. So we're saying that the 95% of the depth is rigid. So when you have the size of the base plate, this is the remaining of, you know, the plate dimension minus 95% of the depth. But on this direction, we are saying that 80% of the beam width is rigid. So what is left here is just the remainder of the dimension of the plate minus 80% of the beam width. Okay, and that's it. So is there any question? It's 10:20 now. I only have 2 slides here, so let's scroll down. Again, this is it's been mentioned. It's the same slide, just repeated, and this is the same thing. Okay, for the column. It's just the design model for the plate with cantilever length is slightly different. Okay, but then that's it. We're gonna study the example in the second hour, and today it may end a little bit quickly, possible. Is there any question? Quiet. So let me pause the record.